Hello everyone, I'm Hannah Jasmine Santos and welcome back to my YouTube channel. So for today's video, we will now move to our experiment number 8, which is actual application using logic gates. So for this experiment number 8, we will answer following problem that has connection in logic circuits and application of digital circuits. So now let's proceed to our first actual application in this logic gate. So first, a locker has been rented in the bank. Express the process of opening the locker in terms of digital operation. Draw the equivalent circuit and truth table. So here you can see that this is what locker bank look like. So in this locker, people store precious item or important things to them. So locker has two keys to be inserted, this one and this one. So when both of their key is valid, so this key is for that key is for the bank manager. And the other one, which is this one, is for the customer. Okay, so when both of their key is valid, only then the locker opens. So the manager will insert his key and also the customer will insert his key so that it needs to open this bank locker. So in that case, let's say our Y is the locker gate and our A is the bank manager and our B is for the customer. So this logic gate is designed for security. Bank manager alone should not be able to operate the locker, or also if the customer alone without the permission or the key of the manager cannot also open the locker. So this is the real world problem that can apply digital logic design. So here, this is our DLC, which is digital logic circuit. Then in this one, this arrow, we have two arrows for the bank manager and for the customer. So this is our input. Then for the output, our output is should be open or not. So let's say when the output is open, there must be a logic 1, and if not, that should be 0. So two input, we need two input in this case. Manager key, the manager key, valid or not, and also the customer key, valid or not. So we can represent this one by binary digital circuit. If the key is valid, so it is at logic 1, but when it is invalid, it is at logic 0. So let's say that here the manager has a valid key, which is 1, and also the customer has a valid key, which is 1. So our output will be 1 or open. But when the manager has invalid key, that will be 0, and if the customer has also invalid key, that also 0. So the output will be 0. So let's elaborate it through our truth table. So in our truth table, there must be a input A, also input B, and output, which is Y. So if our input is 0 and also our input B is at logic 0, our output now is at logic 0. Okay? And when our manager key is invalid, which is 0, and the customer key is valid, which is 1, our output now will be 0, or the locker will not be open, because in this logic circuit, the logic of this problem is there must be two valid key to be inserted in our locker, which is from the manager and from the customer. So again, when our bank manager has valid key, but our customer has invalid key, the output will not be open, which is 0. Okay? So now when both A and B is valid, which is 1, and also 1, our output Y will be 1. So that is the truth table for this problem, and our Boolean algebra for this one is our Y is equals to A times B, and our programming language in this one is Y is equals to A and B, which means and represent the product, or we need to multiply the input we insert in the locker. So our logic gate that we used in this problem is AND gate, and the electric circuit looks like is this one. Okay, we have 2 input and 1 output, which is Y, and our input is A and B, which is the bank manager and the customer. So for the simulation of this number 1 problem, we will use Logisim software. So in this case, we use AND gate. We will put AND gate here, and 2 input and 1 output, and we will make this number of inputs to 2, and we will connect this one, this input and this input to the AND gate, and we will connect this to the output, and we will label this input as A, B, and the output will be our Y. So let's check the truth table if they are similar. So here our output is 0001, and in the simulation our output in this table is 0001. So they are similar, and our truth table is correct. So let's proceed to our problem number 2. So let's proceed in the number 2. Draw the truth table and a circuit to realize each expression using AND gates or gates and inverter. Use Logas or any software simulation. So in this part, we will simulate, and we will create circuit and truth table for this expression. So we will use Logisim for this one. So first, this Y expression, Y output. So there is not A times B plus A times not B, and overall is not. So again, using this AND gate, so an AND gate, the logic or Boolean expression given for digital logic AND gate is that for logical multiplication. which is denoted by a single dot, as you can see earlier. Then, the logic or Boolean expression given for the digital OR gate, this one, is logical addition, which is denoted by a single dot. So, here, we will decrease the number of input to 2. So, in this A, not A, we have here 2 input, which is A and letter B. So, this is A. This is A. And this input is B. So, our output is Y. So, we have first the not A. So, it is, we need this one, not gate. So, we will connect this input A to this NOT gate, and this NOT gate is connected in our AND gate. So our input B is connected to this one. Okay. So now we have this equation, and we will now make this second one, which is A times not B. So A, we need AND gate again, so we will connect this. We need to connect this one to this input. Then here we need another NOT gate because our input B is not B. So we will connect this one to this NOT gate, and we will connect this NOT gate to this AND gate. And after that, we will connect this to AND gate because there is a plus sign here. So we will connect this one. And also this to this second input. Then we will connect this OR gate to NOT gate. Why? Because there is a NOT here overall. So let's connect this NOT gate, and we will connect this in our output. Okay, so for this we will check here, analyze circuit. Then this is our expression, like what you see here. There is overall NOT, then NOT A, B plus A, NOT B. Then our table for this one is when we input logic 0 in our both input, our output then is at logic 1. But if there is only at logic 1 in the input, our logic our output will be at logic 0, like here and in here. Then when we input 2 at logic 1 in our input A and B, so our output then is at logic 1. So that is for our first expression. So let's save this one. For Y output. So next will be this output, which is Z. So let's make a new. So in this one, we have 3 input, which is A, B, and C. So let's input here. We will rename this, we will label this at A. This one is B, and the last one, the last input is C. So we have only one output, which is Z. So our output will be here. We will label this at Z. Then you can see that there is A plus B plus not C. So we need an OR gate, because OR gate is for the addition. So here, okay, so we will make this the number of input will be 3. So here again, we will connect the A and we will connect the input B. And for the input C, that is a NOT C, so we will put a NOT gate. So our input C will be connected in our NOT gate, and our NOT gate will be connected in the OR gate. So we have this one. Then we have this A plus NOT B. So we have again an OR gate for this, and we need only 2. So the number of input in this is 2. So we will connect the A here in the input. Then we will put a NOT gate, because here our B is NOT. So this is our B. Let's connect this, and we will connect this in our OR gate. So next one, we have 3 input again, and we will add again an OR gate. So our input A is the NOT, so we will input NOT here and make this one 3 input. Then we will connect this A in the NOT, and we will connect the NOT gate in the input of this OR gate. Then the second one, the B and the C is connected, so we will connect the B here and also the input C. So the connection, we will need an AND gate, because the 3 expression is have an single dot which is multiply. So we have input, 3 input. 3 is the number of the input. So let's connect this to this one and here. And we will connect this AND gate in our output Z. So let's check what is the expression if they are similar. So let's check. So you can see here A plus B plus not C, then A plus B, A plus not B, not A plus B plus C. So they are similar. So the table for this one is this. So let's save this as Z output. In this one, A, B plus not C. So we have 3 input, which is A, B, and C, equals to our 1 output, which is W. Then I will label this as A and B and C. Okay, so here our A and B is have a single dot represent an AND gate. So let's have this one and make this as 2 input. Because it only needs the input A and B. And B we will connect, so that is then plus not C. So we need here an OR gate and also a NOT gate because there is a NOT in C. So let's have this one and make this one. The number of input is 2. So here, and the NOT gate will be connected in this OR gate, and this one is connected. Then our output now is connected in our OR gate. So let's check if that is correct. So here, W is equal to A, B plus not C. So our table for this one is here. So let's proceed in our fourth by saving first this one, W output. And let's proceed in our last expression in this number 2 by creating new file. Okay, so for this one we have 2 input and 1 output. So our input is A and B. So we will label this again. And our output is X. So here, there is not A times B and overall not, then plus A times not B, overall not. So let's see, we need an AND gate for this one and NOT gate because our A is not. So let's make this 2. So we will connect this to this one and our NOT gate will be connected in our AND gate. Then our B is connected also to our AND gate. Then again, there is an AND gate where the letter B is not. So let's make this 2 input, and we need again the NOT gate because our B is not. So let's connect this A to this one, and let's connect this B to the NOT gate, and we will connect the NOT gate to this input. And overall, this one has plus sign here, so we need an OR gate that have 2 input. We will connect this one and this one. So you can see here that the NOT in the top is by NOT A and B and A and NOT B. So we will adjust this by putting first the NOT gate, 2 NOT gate, because this is the first one and the second one. So we will connect this to the NOT gate. Also this one. And we will connect this OR gate to our output. So let's check if the expression is similar in the given expression. So let's check. Our X is equals to NOT of NOT A and B plus NOT of A NOT B. So here you can see that there is an also NOT in the top like this one, and NOT in A and NOT in B. So that is correct. So back to this one. The truth table for this is this one. So now we have done in the number 2 the 4 expression. So let's proceed to the actual application number 3. So let's save this. So for the third one, a bulb in a staircase has two switches. One switch being at the ground floor and the other one of the first floor. At the first floor, the bulb can be turned on and also can be turned off by and one of the switches, irrespective of the state of the other switch. The logic of switching of the bulb resembles. Express the process in terms of digital operation. Use software simulation. Draw the schematic diagram and truth table. So we need to paint again. Here is the problem. So there is a first floor and the ground floor. So let's say that this is our first floor. And this one is our ground floor. And there is a staircase. So let's draw. And there is a bulb in the staircase. So let's put a bulb here. Let's say that is the bulb. And this is the staircase. So what we need here is the bulb can be turned on and also can be turned off by and one of the switch, irrespective of the state of the other switch. So we need turn on mechanism of the bulb here. Let's say that this first floor is our switch 1 and this ground is our switch 2, and our output is the bulb. So let's make a truth table, S2, and the bulb. If the bulb is, if the switch 1 is turned off and our switch 2 is turned off also, our output will be 0. Then if switch 1 is logic 0 or turn off, but our switch 2 is at logic 1 which is turned on, our output now, or our bulb will be turned on. So that is at logic 1. And when our switch 1 is at logic 1 and our switch 2 is at logic 0, our output or our bulb will be turned on. Then if the 2 is at logic 1, that will be turn 0. So in this case, let's say not S1 multiply by S2 plus S1 and not S2. So we will consider only this case, because in the problem the bulb can be turned on and also turned off by one of the switch, or can be equal to S1 and this sign to S2. So that is XOR gate. So express the process in terms of digital operation, use software simulation, draw the schematic diagram and truth table. So we will use Logisim for this one. So we clarify that that is XOR gate, so we will put XOR gate and 2 input, which is S1 and S2. Here is the S1 and here is the S2. We will connect this in our XOR gate, and our output is B, that is represent the bulb. So let's check if the expression and the table is correct. So here, let's see if it's similar to what we have done earlier. So the 0 is equal to 0, then 0 1 is equal to logic 1, then 1 0 is equal also to at logic 1, then input 1 1 will have an output 0. So the truth table for this one is this one, and this is the diagram. So that's all for the number 3 actual application of logic gates in this digital circuit. So we are now done in this experiment number 8.
So that's all for today. I hope you learned something new about this experiment number 8, actual application using logic gates, and also it helps you to solve and answer the following problem including in this experiment. Don't forget to subscribe and like this video. Thank you.